Okay, generally chemistry students, this is going to be that acid and base review guide that you guys got, and go over some of the conceptual stuff as well as the calculations for titration. So this is the beginning stuff that we worked at a couple weeks ago. Some of the stuff that maybe you forgot and need a refresher on before you take that test. First of all, we have characteristics of acids and bases. And these are the ones that we used in class. And so this is review actually from first semester as well as this unit. So acids have a sour taste, bases have a bitter taste. Acids have a pH below 7, bases have a pH above 7. Bases also have a feel, they feel slippery, kind of like soap, where acids don't have a distinctive feel, so we don't use that as one of the indicators for acids. They both conduct electricity, and they both change the indicator of acid-base indicators, the colors of them. And so, like we use the phenolphthalein in the titration lab, that's an indicator that turns pink when it's a base, and it's colorless when it's an acid. And there are lots of different kinds of indicators, and so they work both ways. Now, the other one for the acids is that they react with some metals to produce hydrogen gas. So that's an important difference here. So they kind of all have the same types of things, some opposites, like the taste, sour, bitter, but this one for the acids, the production of hydrogen gas with metals, and then this one over here for the base, the slippery, those are the ones that are different. All right, so we can go on to this statement here, which has to do with the hydrogen ion concentration, hydroxide ion concentration. So we want to remember that in an acidic or a basic solution, we're measuring the hydrogen ion concentration and the hydroxide ion concentration, because in an aqueous solution, we have both of those things present. And if they are in equal quantities, like this first statement, it's a neutral solution. If we end up with more hydrogen ions than hydroxide ions, then it's acidic. If we end up with more hydroxide ions than the hydrogen ions, it's basic. So we can set up a general statement here with symbols and math rather than using a paragraph. We see the equal sign, it's neutral. Greater than sign for hydrogen ions, it's acidic. Oh, I missed one here. I missed that one where I was doing this. It's going to be the basic. So there's the basic solution. All right, for question number 3, when we're identifying those as either acidic, basic, or neutral, there's actually 2 different ways that we can do that kind of a problem. And so I think there's one that's easier than the other. And that means that we're going to come back to it later. And so I'm going to question number 4 next, and I'll come back to question number 3. So the dissociation processes, remember that when dissociation processes, we have the acid or base split up into its ions. And it's also called an ionization process. So the hydrochloric acid, HCl, splits up into its hydrogen ion and chlorine ion. Same thing with the nitric acid, hydrogen ions, nitrate ions. The polyatomic ions, those do not split apart. I have students that will do this, H plus N plus oxygen, and then they try to figure out the charges on these and try to balance it in some way. So this is wrong. The polyatomic ions split apart. A really easy way to tell if you did this correctly or not, or at least you know that you didn't do it wrong, is if you have 2 answers for your product. You have the hydrogen and then the other thing, or hydroxide on the other thing. If you have more than 2 things on the product side, you're wrong. So here's the acetic acid, this is vinegar, hydrogen, and then this is the acetate ion. Then we have sodium and hydroxide. Remember the acids, we split up between the hydrogen and whatever's there. Hydrogen has a positive charge. We can figure out what the other thing is based on that. Then we have sodium, aluminum, and potassium. We split up before the hydroxide. So we end up with that hydroxide has a negative charge, which means the other one has to have a positive charge. We use the charge values to figure out the individual charges. So the overall charge has to be 0. This is -1, that has to be a +1. Same thing here. If this is -1, since there's 3 of them, That's a -3. This has to be +3. Gets us 0. Notice that 3 is out front now. That means this is no longer bonded together. Here it indicates bonding. Here it's no longer bonded because they're ions. And we put the 3 out in front. Potassium and hydroxide splits up just like the sodium and hydroxide. For neutralization reactions, we have our water in every single one of these. So it produces water, and then whatever is left. So in order to make the water, remember we use everything from the acid that makes the acid, and everything in the base that makes it the base. So we're left with magnesium and nitrate. So we put those two things together and make sure they have the correct chemical formula. Magnesium is +2. Nitrate is -1. We know that because of where this one is on the periodic table. And this is -1 because we know the hydrogen's +1. That's -1, -1. So we have to have 2 of those for this to equal 0. This one's a little bit simpler. We produce the water. Now we have the potassium and the chlorine left. So we can go ahead and get rid of that, get rid of that. Potassium goes first because it's the metal. Potassium chloride is +1, -1. The sulfuric acid and the sodium hydroxide, again, the hydrogens go away. Hydroxides go away. We're left with sodium. Sodium goes first, it's the metal, and sulfate. We know that sodium is +1 because the hydroxide is a -1, and we know that the sulfate has to be a -2 because the hydrogen's a +1. So we have 2 of those. This has to be a -2. So we have to have the 2 subscript there. All right. Now on to pH. There are 3 different equations we need for pH. We have the first one, pH is equal to -log the hydrogen ion concentration. pOH is equal to -log the hydroxide ion concentration. And then pH plus pOH. The very last one there. And so all of these will be given on the exam, but they're ones that we use enough that you should just have them memorized. If it's an acid, we use the pH equation. If it's a base, we use the pOH equation. And if we want pH, then we have to use the final equation to get that. So let's look at these and see what I mean. We have 0.0035. If I go through and calculate that, I end up with that's -log 0.0035 equals 2.46. If we have a base, instead we're going to use pOH is equal to -log of 6.1 that gets us 5.2. So if we want pH, change this color, we have to take 14 minus 5.2. 8.78. So that's how we get the pH of bases. So we have another acid here. .09, another base, 11.64. So there are those. Now we get into the titration stuff, where this will be mostly fresh in your mind, or more fresh in your mind, than the pH and neutralization reactions. So, purpose, quantitatively determine the unknown of a solution. So we're looking specifically at that concentration. We're looking for molarity. The purpose of the indicator simply is to tell us when to stop titrating, but it also tells us that the moles of the known equal the moles of the unknown. And so that's our mole ratio there. And we use phenolphthalein for this. And at that light pink color, we are at our end point, and we're at our neutralization point, which means that the moles are equal to the moles. Burettes are used because they can accurately and precisely dispense a volume of liquid or of a solution. The primary standard is going to be the KHP. It's some kind of a known substance, usually an acid that's a solid that can be massed. That way we can convert it into moles. So we know specifically its quantity. The secondary standard is what we use, or what we find by using the primary standard. So it's some kind of a solution that has a concentration that we need the exact concentration for. And that's calculated using the primary standard. We use sodium hydroxide. The titrant and the analyte. The titrant is the thing that we know, and it's in the burette, sodium hydroxide. And the analyte is the thing that we don't know. It's in the flask. That was the vinegar. All right, so we have the calculations here. These are going to be for a couple different titration problems and some more practice on that. Notice that it gives you the information in a little bit different format than how we've seen before. It's just all a word problem. There isn't any kind of just data given to us, so we need to read very carefully and figure out how to break this down. So we have a titration between hydrochloric acid and potassium hydroxide. That molarity of the hydrochloric acid is 0.8551. And so I'm going to go ahead and just take that and write it right below the hydrochloric acid. And then we have 5.50 molar of the potassium or milliliters of the potassium hydroxide in a flask. So I'm going to put 5.5 milliliters there. So we have this concentration of the hydrochloric acid, this volume of the potassium hydroxide, and we have 17.56 milliliters of the hydrochloric acid. So if it takes that much to reach the end point, so I'm going to put this here as well, 17.56 milliliters. Now we can look at what we're asked for, the concentration of potassium hydroxide. So that is our unknown. Once we take all of this and put it into this here, where we can see it all together, it makes the problem significantly easier. So now we can look at our different steps for our stoichiometry. We have our first step, which is to convert to moles. Let's put an arrow, moles. So we have molarity, moles over liter. And so this is going to be for hydrochloric acid, because that's what we have to be able to calculate moles. We have a molarity, we have a volume. Notice I converted the 17.56 milliliters into liters. And if we go through that process, we end up with 0.015 moles of hydrochloric acid. Now the step 2 is the mole ratio. So it is a 1 to 1 mole ratio. So whatever moles of hydrochloric acid is going to be moles of the sodium or potassium hydroxide. So that's what we have there. Now step 3 is to convert out of moles. So we have moles to whatever we're trying to find, in this case, a concentration. So we can still use the same molarity equation. Molarity is equal to 0.015 moles of the potassium hydroxide over 0.0055 liters. So there's the 5.5 milliliters, converts to liters. We end up with a final value of 2.73 molar potassium hydroxide. Yeah. We need one more number here. 0. Your answer needs to be exactly like mine. Let's go on to the next one and the last one. We have another titration here. Again, it's given to us in a word form, so we're going to break this down so we can see all of our information. We have strontium hydroxide. Notice this is just a little bit different because it has a subscript 2. So we want to keep track of that when we do our mole ratio. And then we can look at the nitric acid here as our known, I believe. So let's look through this. We have the concentration of the base is unknown, and you're trying to figure out the concentration of the acid. The known concentration of strontium hydroxide is 0.05582. So I'm organizing this again. And titrated against the unknown nitric acid. We have 25 milliliters of the nitric acid with 42.56 milliliters of the strontium hydroxide that was required. So now we have all the information organized again with the unknown that we're looking for. Same problem as we did previously, only one little difference, and that's that it's a 1:2 ratio. We haven't done really any practice problems like this in titration with a 1:2 ratio. We've done plenty of stoichiometry problems that have a 1:2 ratio. So let's look at our 3 different steps again. 1, 2, 3. First step is still going to be the molarity step. We're converting 2 moles. We can multiply those together, get 0.00238. Now we're going to figure out the moles of the nitric acid, because that's what we're trying to get to. So 1:2 ratio, so I can't just say that they equal each other. I have to go through my step. So we multiply those together, we end up with 0.00475. And now we can use this to figure out the concentration of nitric acid. Notice that this is going to be the SrOH2. This is going from the the strontium hydroxide, SrOH2, to the nitric acid. That's our stoichiometry step, and then we have the conversion here. So we have molarity 0.00475 divided by the 25 milliliters is equal to 0.1901 molar nitric acid. So that's our final answer. All right, that's all.